All right, so we're going to move on to Introduction to Thermodynamics. And thermodynamics is a branch of physics that's based on the fundamental laws of nature concerning energy and mechanical work. Thermo means heat, and dynamic means movement. However, thermodynamic encompasses much more than just the study of heat transfer. All right, to get started, rub your hands together for 15 seconds. Are your hands warm? This is thermal energy. Thermal energy is energy that is generated and measured by heat. Thermal energy is the internal energy of a body or substance, resulting from the vibration and movement of atoms and molecules. You can think of these atoms and molecules as bumper cars. If the cars could only travel at a snail's pace, few collisions or vibrations would ever occur. However, if the cars could travel at the speed of a race car, the resulting collisions or vibrations would be astounding. The thermal energy of a substance is measured by the intensity of these vibrations. Let's take another look at the bumper car example. Each bumper car represents an atom or molecule inside an object or a substance. If the bumper car does not move, no work is being done and no energy is being transferred. When the bumper cars are moving, they contain kinetic energy. If they bump into one another, the kinetic energy of one car is transferred to the other. The faster the bumper cars move, the more work that is being done and the more energy that's being transferred. There's approximately 7.9 times 10 to the 24th molecules of water in 1 cup of water. Because it would be impossible to keep track of all the kinetic energy of each molecule, measuring the temperature of water is actually the average kinetic energy of these molecules. When the temperature increases, those molecules vibrate, spin, and slam against each other more often and with greater force. As the temperature of the water decreases, the average kinetic energy of these molecules decreases as well. It's important to understand the difference between thermal energy and temperature. Thermal energy is kinetic energy in transit from one object to another due to temperature changes. Temperature is the average kinetic energy of particles in an object, not the total amount of kinetic energy. If a 100-gram mass is at the same temperature as a 200-gram mass, the average kinetic energy of the particles in both masses is the same. However, the total amount of kinetic energy in the 200-gram mass is twice the amount in the 100-gram mass. As I previously stated, since matter is made up of atoms in motion or kinetic energy, an increase in temperature is going to increase that motion, and a decrease in temperature is going to decrease that motion. Everything in the universe has some thermal energy because an absence of thermal energy would imply that the temperature is absolute zero. Absolute zero is when all kinetic energy is removed from an object, or put simply, the atoms stop moving. The Fahrenheit scale sets the boiling of water equal to 212 degrees and the freezing point of water equal to 32 degrees, whereas the Celsius scale sets the boiling point of water equal to 100 degrees and the freezing point of water equal to 0 degrees. Developed by Scottish physicist William Thomson, the Kelvin scale is widely used by scientists and engineers. Each degree on the scale is called a Kelvin and is represented by the capital letter K. By international agreement, the Kelvin is never referred to as degrees Kelvin or Kelvin degrees. The magnitude of 1 Kelvin is equal to that of 1 degree Celsius. The difference between the boiling and freezing points of water is 100 degrees Celsius to 100 Kelvin. Science has proven that there is an absolute lowest temperature, which is called absolute zero. This is the lowest point on the Kelvin scale, and it is defined as 0 Kelvin. On the Kelvin scale, the freezing point of water is 237 Kelvin, so to convert degrees Celsius to Kelvin, you must add 273 to the Celsius temperature. On this slide, there is a few temperature conversion formulas that you're responsible for knowing. Take a few minutes to get acquainted with them and make sure you have them written down in your notes. Thermodynamics is the study of the effects of work, heat, and energy on a system. Put another way, nothing happens without heat flow. A thermodynamic system is a quantity of matter or a region in space that's separated by a boundary from its surroundings. For example, the coffee inside a thermos is a thermodynamic system. Everything outside the thermos is the surroundings. The boundary is the thermos, which is located between the system and the surroundings. Thermodynamic systems can be open or closed. An open thermodynamic system allows mass and energy to flow freely through the boundary. Your lungs are an example of an open thermodynamic system. Air that enters your lungs is warmed by your body and is eventually pulled out. A closed thermodynamic system does not allow mass to cross the boundary from the system to its surroundings, or vice versa, but it does allow energy to be transferred across the boundary in the form of work or heat. An example of a closed thermodynamic system would be a light bulb. Electrical energy, light, and heat pass through the boundary, but the mass contained within the bulb cannot pass through the boundary. Thermal equilibrium is obtained when touching objects within a system reach the same temperature. When thermal equilibrium is reached and there's no heat flow between objects, the system loses its ability to do work. The zeroth law of thermodynamics states that if two systems are separately found to be in thermal equilibrium with a third system, the first two systems are in thermal equilibrium with each other. That is, all three systems are at the same temperature. This concept is similar to the transitive property found in mathematics. If A equals B and B equals C, then A has to also equal C. Heat transfer can occur in three forms: conduction, convection, and radiation. We're going to talk about all three of these on this slide. Starting with conduction. Conduction is the transfer of heat by the movement of warm matter. For example, a metal spoon placed in a hot cup of soup will feel warm to your hand because the heat from the soup is conducted through the spoon. When a cast iron pan is placed over an open flame, heat slowly moves up the handle towards the cooler end. On a molecular level, the molecules in the pan initially have much more kinetic energy than the molecules at the end of the handle. These molecules are vibrating rapidly, colliding with other molecules next to them. A molecule's or atom's individual kinetic energy is transferred up the handle of the pan as faster moving atoms and molecules transfer their energy to slower moving atoms and molecules. These in turn vibrate faster, causing adjacent slower molecules farther up the handle to also vibrate faster. This process continues as kinetic energy of the molecules is transferred all the way up to the end of the handle. This process is known as thermal conduction. The transfer of heat through the movement of warm matter in a fluid is called convection. It is a process by which, in a fluid being heated, the warmer part of the mass will rise and the cooler portion will sink. For example, warm air rises from the land and moving over the cooler waters of the sea where it begins to cool. At night, the process is reversed as the warmer water of the sea heats the air above, causing the air to rise and move toward the cooler land where the air is cool. The convection currents will continue until the land and water reach the same temperature. And with radiation, understand that you really can't escape radiation and its effects. When you have a warm meal from the microwave, or you play outside on a sunny day, or if you happen to get an x-ray, or you're listening to the radio, you're always being bombarded with radiation. Radiation refers to energy transferred by electromagnetic waves. Radiation has the ability to transfer energy through empty space, unlike convection and conduction, which both need matter to transfer energy. This energy travels at the speed of light, and one of the most common examples of this heat transferred is from the sun to the earth. So we've spent a lot of time talking about energy flow and transformations today. The first law of thermodynamics, known as the conservation of energy, states that the total amount of energy never changes. Energy cannot be created or destroyed. This means that the total amount of energy entering a system must equal the total amount of energy exiting a system. Think energy in equals energy out. Thermal energy can be increased within a system, however, by adding thermal energy in the form of heat or by performing work in a system. So as we've seen with the first law of thermodynamics, energy can flow and it can change its form, but the total amount of energy never changes. Consider this example. As we use a bicycle pump, we're applying mechanical energy into a system. But that mechanical energy is converted into thermal energy as we do work by pushing up and down on the piston and compressing the air. The first law of thermodynamics states that the total increase in internal energy of the system has to be equal to the applied mechanical energy. If this is true, then why are we so concerned about using less energy? The answer to this question lies in the second law of thermodynamics. Trying to collect and store usable heat is like trying to carry water using a leaky bucket. Both will eventually escape from their containers. Imagine you ran out of hot water to take a bath, and your only option is to fill the bathtub with ice water. Your body temperature is roughly 98.6 degrees Fahrenheit. Let's say that the temperature of the water is only 50 degrees Fahrenheit. As you probably have guessed, when you get into the bath, you're going to become very cold. But why? The answer is heat flow. Heat always flows from hot to cold. Because the temperature of your body is higher than the water temperature, the heat will flow from your body into the water. Over time, the water temperature will increase, but your body temperature will decrease. Why do you wear shorts in the summertime and long pants in the winter? The answer to this question again is heat flow. If it's really cold outside and your body temperature is higher than the air temperature, then the heat your body produces will flow into the air. To prevent the heat from escaping, you can wear pants, a jacket, and a hat and gloves. If it's warm outside and your body temperature is closer to the air temperature, you want your body to easily transfer heat to the air. The solution to this problem is to expose more of your skin to the air by wearing shorts and t-shirts. When you touch a frozen pizza with your hand, again, thermal energy flows from your hand to the pizza, which is why touching the frozen pizza feels cold. But when you touch a cooked pizza with your hand, thermal energy flows from the pizza to your hand, which is why it feels hot to the touch. So the second law of thermodynamics we learned states that thermal energy flows from hot to cold. But it also explains why energy cannot be reused again and again. It states that as energy changes forms, its usefulness decreases, as we will always lose some of it to heat. Entropy is the measure of the amount of unusable energy in a system. The total amount of energy in the world does not change, but the availability of that energy constantly decreases. The second law of thermodynamics also states that the efficiency of any system must always be less than 100%. Entropy is a measure of how evenly distributed heat is within a system. A general statement is the idea that there is a preferred direction for any process. A system will tend to go from order to disorder. For example, firewood has a low entropy, which means the atoms are in order when stacked, and a high entropy when the atoms are in disorder when it's burning. And the third law of thermodynamics simply states that it's impossible to reach a temperature of absolute zero. It is possible to come close to absolute zero, but it's not possible to actually reach it by any process or series of processes. A loophole in the second law of thermodynamics would allow a system to be 100% efficient if absolute zero could be reached, but the third law of thermodynamics closes this loophole. In order to calculate how much heat energy is required to change the temperature of a substance, you must know three things. 1, the mass of the substance. 2, the desired change in temperature of that substance. And 3, the specific heat capacity of the substance. The specific heat capacity is recognized by the lowercase letter c, and it's the measure of the substance's ability to absorb thermal energy. In essence, it is the heat required to raise the temperature of the mass of a given substance by a given amount, which is usually 1 degree. As you can see in the provided equation, the amount of heat, Q, represented by capital letter Q, is equal to mass, m, of the substance times the specific heat capacity times the substance's change in temperature, delta T. Please make sure you make note of all of the units that are represented by each of these variables. Here are a few thermal energy transfer equations that you're responsible for knowing. First one is the rate of energy transfer, P, is equivalent to my energy transfer, Q, divided by delta small t, which is the change in time. Another equation for calculating the rate of energy transfer, P, is equivalent to K, which is the thermal conductivity of the substance, times the area of that thermal conductivity, times the delta big T, which is the change in temperature, all divided by the thickness of the material. And if I wanted to calculate thermal conductivity, I could manipulate this middle equation here and solve for K. And if I did that, I would get P times L, so the rate of energy transferred times the thickness of the material divided by the area of the thermal conductivity times delta big T, which again is the difference in temperature. Again, make note of the units for each of these individual variables for these respective equations. Let's look at an example of calculating energy transfer. It says here in this problem, calculate the energy transferred when a block of aluminum at 80 degrees Celsius is placed in 1 kilogram or 1 liter of water at 25 degrees Celsius if the final temperature becomes 30 degrees Celsius. All right, so let's kind of visualize what's going on here. If you look at the picture to the right, that will help you kind of visualize this. We have a metal block made of aluminum. It's 80 degrees Celsius. I'm dropping it into a cooler temperature of water at 25 degrees Celsius. Eventually, the final temperature of the two are going to even out to 30 degrees Celsius. So this is where we're at. Step 1, list out your knowns. So what was given to us? We knew the mass of the water is 1 kilogram. Your specific heat capacity is going to be a specific number that's designated for each particular substance. So for water, the specific heat capacity is always 4,181. The change in temperature of the water, delta T, is going to be 30 degrees minus 25 degrees, which is 5 degrees Celsius as my temperature change. And then the specific heat capacity of aluminum, that was not given to us, but you could certainly look this up. But in any question moving forward on an assessment, the specific heat capacity values will always be given to you. So for aluminum, it's 900. The change in temperature for aluminum would be it's going from 80 degrees down to 30 degrees. So there was a 50 degrees in Celsius change in temperature. Step 2 is to list your unknown values. We have the amount of energy transferred, which is Q, and the mass of the aluminum block that we need to find. Step 3 is once we've identified what we need to find, we need to come up with which equations we're going to use in order to solve for those unknowns. So we have Q equals MCAT, and we know that the energy transferred from aluminum has to equal the energy transferred to the water and vice versa. So step 4, let's go ahead and solve for the energy transferred in water. So to calculate the energy transferred in water, we'll use Q equals MCAT. So it's our mass times our specific heat capacity times our change in temperature. So the mass was given to us as 1 kilogram. Our specific heat capacity is 4,181, and our change in temperature is 5 degrees Celsius. If I multiply those three values together, we get our energy transferred of 21,000 joules gained. And this should make sense because think about it. The aluminum block had a higher temperature than the water. And so when I drop that aluminum block into the water, the aluminum block is losing joules, it's losing energy, and the water is gaining energy. So in step 5, we can now solve for the mass of the aluminum block. So we know that the energy transfer from our aluminum block has to equal the energy transfer to the water. The aluminum block is losing energy and the water is gaining energy. And we know it has to equal approximately 21,000 joules. So to calculate the mass of the aluminum block, I can take my energy transferred from the aluminum block divided by the specific heat capacity and divided as well by the change in temperature. So 21,000 joules divided by 900 times 50 degrees Celsius, and I get 0.46 kilograms, which is equivalent to 460 grams. In this next example, we're asked to calculate the energy transfer in a wall section measuring 2 meters by 1 meter by 0.04 meters thick with the thermal conductivity of 0.10. Tells us that the opposing sides of the wall section have a temperature of 10 degrees Celsius and 5 degrees Celsius after 1 hour. So again, step 1, take a look at that problem and let's list out all of our known values. We know that the area of thermal conductivity is length times width, so 2 meters times 1 meter, which is 2 meters squared. Thermal conductivity that was given to us was 0.10. The thickness of the material was 0.04. The change in temperature, we're going from 10 degrees to 5 degrees, so that's a change in temperature of 5 degrees Celsius. And then in our change in time, we need to convert that 1 hour to seconds, so 60 times 60 is 3,600 seconds. Step 2, let's list out all of our unknown values. We don't know P, which is the rate of energy transfer, and we don't know Q, which is the amount of energy being transferred. So step 3, once we've identified our unknown values, let's list out our equations that we're going to use to find those unknown values. So we have P equals Q over delta small t, and P equals K times A times delta big T over L. So step 4, we can solve for Q by manipulating that first equation. If I cross multiply, I get Q equals P times delta small t. And then I can replace P with the second formula, K times A times delta big T divided by L. So step 6 is to apply our known values so that we can solve for Q, which is the amount of energy being transferred. So K, remember, is the thermal conductivity, which is 0.10. Area was 2 meters squared. Delta big T was the change in temperature, which was 5 degrees Celsius. Divide that by our thickness of the material, which was 0.04 meters, and then we can times it by our change in time, which was 3,600 seconds, and we get approximately 90,000 joules. One of the most important material performance measures is U value, also known as the U factor, which measures the insulating characteristic of that material and how much heat flow or heat loss occurs through the material due to the difference between indoor and outdoor temperatures. U values can tell you how much an insulated material will hold in heat or cool air. The lower the number, the better the insulating performance. U values generally range from 0.1, which is very little heat loss, to 1.0, which is high heat loss. To calculate the U value, you take P, the rate of the energy being transferred, and divide it by the area times the change in temperature. And then we have the R value, which is the measure of a material's ability to resist heat. The higher the R value, the higher the resistance. There is a mathematical relationship between U values and R values. They are mathematical reciprocals of each other. Thus, while lower U values indicate better insulating performance, higher R values indicate better thermal resistance. To calculate the R value, simply divide 1 by the U value figure. For example, a U value of 0.10 equals an R value of 10, since 1 divided by 0.10 is 10. To calculate the U value, divide 1 by the R value. A 3.45 R value is equivalent to a U value of 0.29. When you're dealing with a bunch of different materials acting as thermal resistance, we have what's called the bulk R value. And to find the bulk R value, you find the individual R values of each of the objects and simply add those together, and that will give you your total R value. Consider this example where we're asked to determine the R value of the wall cavity below. So our wall cavity looks like this, and we have several different materials. We have the R value of 0.56 for the 5/8 inch drywall. We have the fiberglass bat, which has an R value of 19. We have the 1 inch foil-faced polyisocyanurate, which has an R value of 7.20. We have this airspace, 1 inch airspace, which has an R value of 0.17. And then we have the brick wall, which has an R value of 0.8. Now, these R values, again, will always be given to you. You don't need to know them, memorize them, or anything like that. So if I add those R values together, my bulk R value for the wall cavity is 27.7. Now, the next question on the right here says, what's the R value at the stud location? So at the stud location, right here, if I take a cross-sectional view of it, I have the 5/8 inch drywall, R value of 0.56. We have the R value of the 2x6 construction, which has a R value of 6.88. We have the 1 inch foil-faced polyisocyanurate, which has an R value of 7.20. We have the gap in the airspace, which has an R value of 0.17. And then we have, again, the brick wall, which has an R value of 0.8. So if I add those values together, I get an R value of 15.6. And in our final example, we're going to look at calculating the radiated energy transfer. So again, radiation is the process by which energy is transmitted through a medium, including empty space, unlike convection or conduction, as electromagnetic waves. The formula we're going to apply for calculating radiated energy transfer is called Stefan's law. And Stefan's law states that all objects lose and gain thermal energy by electromagnetic radiation. Here's our formula. So P represents the radiated energy transfer. Sigma is Stefan's constant, and it's always going to be this super small number, 5.6696 times 10 to the negative 8th. Area, we have our emissivity constant, and that's going to be a value that represents the ability for a surface to emit radiant energy. And then this time with temperature changes, it needs to be in Kelvin. So make note of that. And it's going to be my second temperature raised to the fourth minus my first temperature raised to the fourth. Again, both of those temperatures need to be in Kelvin. So let's take a look at the example. Prior to dressing for school, a student watches the morning weather to decide what clothes to wear. The bedroom is 65 degrees Fahrenheit and the student's skin is 91.4 degrees Fahrenheit. Determine the net energy transfer from the student's body during the 15 minutes spent watching the morning weather. They note that the skin emissivity is 0.90 and the surface area of the student somehow is 1.30 square meters. So step 1, list out our values. We have area, A, is equivalent to 1.30 square meters. Our emissivity constant was 0.90. Stefan's constant for sigma never changes, 5.6696 times 10 to the negative 8, super small number. Our bedroom temperature was 65 degrees Fahrenheit. Our skin temperature was 91.4 degrees Fahrenheit. Always make the bigger number, the higher temperature, temperature 2, the lower temperature, temperature 1. And then to convert, we need to convert Fahrenheit to Kelvin, remember. So here's your formula for converting to Kelvin when given Fahrenheit. So the temperature in Kelvin is equivalent to 5/9 times the temperature in Fahrenheit plus 460. And our change in time, delta small t, was 15 minutes. We need to convert that to seconds, which would be 900 seconds. Step 2, let's go ahead and list out our unknown values. So we have P, which is the rate of energy transferred, and Q is the amount of energy actually being transferred. Step 3, figure out which equations to use to solve for those unknown values. So we have Stefan's law, P net equals sigma times A times E times T to the fourth minus our second temperature to the fourth. Again, higher temperature goes first. And then to calculate our energy transferred Q, it's going to be P times delta T. So we can apply Stefan's law and plug in our values. So if I convert that 91.4 degrees Fahrenheit to Kelvin, I get approximately 306.15 Kelvin, and 65 degrees Fahrenheit is approximately 291.48 Kelvin. So I can do 306.15 to the fourth minus 291.48 Kelvin to the fourth, and then apply the rest of Stefan's law. So I have Stefan's constant, 5.6696 times 10 to the negative 8th, times my area of 1.30 meters squared, times the emissivity, 0.909, times our change in temperatures of Kelvin, and we get approximately P net equals 103.92 watts. And step 5, we can combine those equations to solve for our energy transferred. So P was 103.92 times the change in time, 900 seconds, and I get an energy transferred of 93,500 joules. So that is telling us in this example, 93,500 joules of energy are being transferred from the student's body during the 15 minutes spent watching the morning weather.